Welcome to homework.
This is chapter 9, problem number 41. In this problem, we are given an initial nucleus that is at rest, which means that its velocity is equal to 0, and that its initial mass is 256 atomic mass units. We are told that afterwards, this nucleus has emitted an alpha particle, and that the alpha particle's kinetic energy is equal to 5 mega electron volts. What you want to know is what is the final kinetic energy of the particle. And we know that it has to have some final kinetic energy because as soon as this has emitted an alpha particle some velocity, it would have had to move back with some velocity of its own, exactly like how when you shoot a gun and as soon as that bullet comes out of the barrel, you have a kickback on it. And this actually gives a big hint of how to solve this problem. That's the same kickback that you get from the gun that the nucleus feels is just the principle of conservation of momentum in action, and that's what we're going to use to solve this problem. So we know that we have that the initial momentum is equal to final momentum, and just like we said before, the initial momentum has to be 0 because the nucleus was at rest. And the final momentum is a product of both the nucleus recoiling and the emitted alpha particle. So I'll denote the mass of the final nucleus and the velocity of that nucleus by a prime, and for the alpha particle, I'll denote it with subscripts alpha. This is a good start, but what we're really interested in is the kinetic energy. So let's remind ourselves what the kinetic energy looks like. The kinetic energy for any particle, point particle that is equal to 1/2 times mv squared. And this doesn't look like this yet, but what we can do is start solving this. And the only thing really missing here is the fact that here we have a square, but we can just square both sides. And I'm writing this in a very specific way. So we can see that we have an m times the v squared on this side and m times the v squared on this side, which is exactly what we want for kinetic energy. So if we multiply both these by 1/2, what we'd be left with is m prime times k prime is equal to m alpha times k alpha. So that's what we have. There should be an alpha right here. And what we're trying to find is k prime, which we can write as m alpha over m prime times k alpha. And now we're almost done. The only thing we need here is that we have to remember that for an alpha particle is just a helium nucleus. And so that is 2 protons and 2 neutrons. And we know that this mass is just approximately 4 atomic mass units, and that our initial mass has to be equal to the mass of the particle that was created plus the mass of that alpha particle, which is that m prime is just equal to mi minus m alpha. So this is something called the principle of conservation of mass. It's only approximately true, but within the context of this problem, in the context of this chapter, it is a very good approximation. We can always assume that it's true. So now we can plug that in. M alpha over m I minus m alpha. And now we have everything we need. We know that the mass of an alpha particle, it's just a helium nucleus with 4 atomic mass units. Mi is equal to what was given before, 256 atomic mass units. K alpha is equal to 5 mega electron volts. So we can plug that in. Times 5 MeV. Notice I didn't put any units on this fraction. It's always good to remind ourselves that we want to be dimensionally constant. And here that is manifestly true because we had a mass over a mass, so it didn't even need to bother writing atomic mass units. And we're multiplying by mega electron volts, which is a unit of energy. And we are left with 0.079. This is approximately mega electron volts for the kinetic energy of our final particle.